What if the universe itself is preparing a doom greater than the jaws of any black hole, an ending so silent, so absolute, that no star, no atom, no memory could survive? For centuries, black holes have stood as the titans of terror. Beasts of collapsed gravity, they swallow light, crush matter, and warp time itself. They were the monsters of Einstein's equations, and later, the dark trophies of telescopes revealed at the hearts of galaxies. Yet as terrifying as they are, they remain local predators, bound to places and horizons. Their hunger is vast, but contained. In the early 20th century, astronomy's triumphs promised clarity. Einstein mapped spacetime with relativity unveiling, a cosmos bound by geometry and gravity. Hubble soon followed, discovering that galaxies drift apart, that the universe itself expands like a vast breath. It seemed a revelation of order, a clockwork cosmos unfolding by predictable laws. But then came the supernova. In 1998, faint explosions at the edges of deep space carried whispers of something unthinkable. Instead of slowing under gravity's pull, the universe was racing apart, faster and faster, as though repelled by an invisible hand. What scientists uncovered was not stability, but betrayal, a hidden force, later named dark energy, accelerating the cosmos toward an uncertain fate. That discovery shattered expectations. It was not gravity that ruled the final word, nor the black holes thought to be the ultimate end. Something deeper, stranger, and infinitely more merciless had been found, woven into the very fabric of space-time. A force not merely devouring stars, but devouring the universe itself. And with that whisper, humanity realized the true monsters of the cosmos may be unseen. The discovery arrived like a crack in the cosmic mirror, a revelation so profound it left even the most cautious scientists unsettled. For decades, it was assumed that the expansion of the universe, first glimpsed by Edwin Hubble, would slow. With time, gravity, though subtle across vast distances, was thought to be the ever-present leash drawing galaxies back together. Tugging on the great architecture of space-time, the cosmos was destined, it seemed, for either eternal balance or a slow collapse into a final embrace. But in 1998, the light of dying stars betrayed that expectation. Type Ia supernova, the standard candles of the universe, revealed something no one had predicted. They were dimmer than they should have been, not because the universe was smaller, but because it was larger, expanding faster than any model of gravity could allow. Instead of slowing, the universe was accelerating, as if pushed by a hidden engine that no one had ever seen, and no one could explain. It was a finding that fractured the comfortable symmetry of cosmology. The fabric of reality was not only stretching, but doing so at an increasing pace, like a wound that refuses to heal. Tearing wider with each passing moment, the implications were staggering. Black holes, once thought to be the ultimate monsters of the cosmos, became suddenly provincial predators confined to singular places. Their event horizons marking territories of destruction. Yet here was a force not confined, not bound, but everywhere. A presence diffused through the very vacuum of space, silent tyrant commanding the entire universe to scatter. It was named with deliberate vagueness, dark energy, not energy is. Physicists understood it, not a familiar particle or field, but something alien, and invisible pressure pushing outward, woven into the geometry of space-time itself. If it remained constant, the universe would stretch into cold isolation, galaxies drifting beyond sight, stars aging and dying in solitude, a cosmos that ends not with fire, but with a long, dimming silence. But what if dark energy grew stronger? What if its repulsion did not remain steady, but accelerated without limit? In that terrifying speculation lies the specter of the Big Rip. In this vision, the expansion would not simply scatter galaxies. It would increase so violently that clusters of galaxies would be torn apart, then galaxies themselves would dissolve, their stars ripped from one another. The next stage would be more intimate and more horrifying. Solar systems would unravel, stars and planets sundered by an unstoppable outward thrust. Even the gravity of a black hole, the most powerful anchor in nature, would be overcome. Event horizons would disintegrate. Singularities themselves would be stripped bare, and the nightmare would not end there. As the acceleration deepened, molecules would be pried apart. Atoms themselves would be pulled until their protons and neutrons could no longer hold together. The very structure of matter, the building blocks of existence, would dissolve. In the final instant before the rip reached completion, space-time itself would unravel, its equations collapsing into meaninglessness. Here, in this imagined future, lies a monster that dwarfs the threat of black holes, for black holes consume, selectively bound to their horizons, feeding on matter that dares stray too near. Dark energy, if it swells into this catastrophic crescendo, does not select. It devours universally. It does not wait for matter to fall toward it. Instead, it tears matter itself apart, everywhere, all at once. A cosmic executioner, merciless and absolute. The shock of 1998 was not merely the discovery of acceleration, but the realization that humanity had uncovered a new layer of fragility in existence. For centuries, black holes had been imagined as the final arbiters of cosmic terror. They bent time, they shredded stars, they promised oblivion at the edge of their horizons. Yet their power was local. Their danger was theatrical. Against the backdrop of accelerating expansion, they seemed suddenly small. Dark energy did not roar, it whispered in silence across the void. It offered no light, no shadow, no event horizon. It could not be escaped because it was not out. There, it was here, in every corner of space, in every stretch of the void. Its dominion was not a region, but the totality of the universe itself, the scientific community. Shaken, searched for metaphors. Some called it Einstein's greatest blunder revived, the cosmological constant he had once introduced and abandoned. Others invoked the ghost of a quantum field, a relic of inflation from the first heartbeat of the Big Bang. Yet all explanations carried the same weight. The discovery marked the beginning of an era where certainty itself had been fractured. If the universe was not slowing, but accelerating, then gravity, the very foundation of cosmic order, was not enough to describe reality. The balance between attraction and repulsion was not what it seemed. Something deeper was at play, something woven into the very equations of existence. For those who first measured it, the shock was personal. Teams of astronomers, scattered across continents, compared their results with disbelief. The error margin shrank, but the result remained. Peer review, skepticism, rival analyses all confirmed the same truth. A force no one had anticipated was commanding the fate of the universe. In time, the scientific community adjusted. Dark energy was absorbed into models, cosmological constants added into equations. But the existential terror could not be so easily muted. It lingered beneath every calculation. The realization that the universe is not a static backdrop, but a fragile theater, subject to forces that remain invisible, unknown, and perhaps uncontrollable. The Big Rip, although speculative, became the most haunting of possibilities. Unlike the Big Crunch, where the universe collapses into a fiery rebirth, or the heat death, where it fades into cold entropy, the Big Rip is personal. It imagines not just galaxies scattered, but the annihilation of structure itself, the erasure of every atom, every law, every remnant of order. In that vision, the cosmos is not consumed by monsters that lurk in shadows. It is consumed by the very emptiness between stars. The void itself becomes the predator. Compared to this, black holes seem merciful. They end with finality, swallowing matter into silence. Dark energy offers no such mercy. It is a slow, accelerating, unraveling, an execution without escape. 1. Written into the geometry of spacetime. For scientists, the shock of 1998 was not only a discovery of expansion, but the recognition that the greatest monster of all may already be awake. Spread across the heavens, guiding every galaxy outward, and if its strength grows, it will not be a predator that ends the universe. It will be the universe itself, tearing apart in obedience to a law written in darkness. The black hole remains a symbol of fear, But beyond its horizon, a greater shadow has fallen, one that no telescope can see and no mind can yet comprehend. The cosmos has always been a mystery written in light. For centuries, astronomers sought truth by capturing photons, those fragile messengers that journey across the void for billions of years. Yet when the whispers of dark energy first surfaced, light alone was not enough. The universe was speaking in subtler ways, woven into the faintest patterns and distortions too delicate for the naked eye. To uncover this hidden force, science required instruments capable not only of seeing farther, but of weighing the unseen. The Hubble Space Telescope became one of the first great tools in this search. Launched in 1990, it orbited above the blur of Earth's atmosphere, delivering clarity no ground-based observatory could rival. Its deep field images tiny fragments of sky revealing thousands of galaxies were not just photographs, but archives of cosmic history. When Hubble joined the effort to measure distant supernova, its precision confirmed what ground-based telescopes had already suspected. The universe was accelerating. The faintness of those explosions was no illusion. Faster and faster, dimming the light of dying stars more than expected. Supernova of type Ia became the yardsticks of this new cosmology. They erupt when a white dwarf star, long cooled and stable, steals matter from a companion until it reaches a critical mass. At that threshold, nuclear fire ignites with catastrophic violence, producing an explosion of nearly uniform brightness. Astronomers call them standard candles because their luminosity is predictable, like identical bulbs placed at different distances. By comparing their intrinsic brightness to their apparent brightness, scientists can calculate how far away they are. It was through these cosmic candles that the truth emerged. The farther the explosion, the faster it was receding. Galaxies were not merely drifting, they were being flung away by something unseen. But supernova were only the beginning. To measure dark energy was to measure the immeasurable, to weigh a force with no mass, to sense a pressure that left no shadow. For this, astronomers turned to other relics of the cosmos, the cosmic microwave. Background, the faint afterglow of the Big Bang, became a silent witness. Discovered accidentally in 1965 by Arno Penzias and Robert Wilson, it is the oldest light in existence, released when the universe was only 380,000 years old. At that time, the primordial plasma cooled enough for photons to travel freely, carrying with them a fossil imprint of the infant cosmos. To the eye, it seems uniform. But satellites like WMAP, launched in 2001, and Planck, launched in 2009, revealed it to be subtly modeled, speckled with fluctuations no larger than a few millionths of a degree. These ripples were not noise. They were the fingerprints of density variations, seeds from which galaxies would grow. By mapping them, cosmologists could infer the geometry of the universe itself. What they found was astonishing. The data showed that the universe was flat on large scales, balanced between collapse and endless expansion. Yet to remain so flat, the cosmos required more than just visible matter and the invisible mass of dark matter. Something else was needed, a contribution that accounted for nearly 70% of the total energy budget. That contribution was dark energy. It was not directly seen in the microwave sky, but its fingerprints were unmistakable, encoded in the shape and distribution of the ripples. Without it, the pattern could not be explained. The Chandra X-ray Observatory joined this effort, turning its gaze toward clusters of galaxies, the largest bound structures in the cosmos. By studying the hot gas within these clusters, Chandra allowed scientists to weigh their mass, but the clusters told a strange story. They were too light to explain the accelerating expansion, too insubstantial to pull back against the repulsive force at work. Once again, the presence of dark energy was implied not by detection, but by absence, by the cosmic arithmetic that refused to balance. As years passed, dedicated surveys emerged to pursue the enigma more directly. The Dark Energy Survey, beginning in 2013, mapped hundreds of millions of galaxies across vast stretches of sky. Its strategy was to trace how structures grow and evolve under the influence of dark energy. By measuring the bending of light through gravitational lensing, by cataloging the distribution of galaxies, the survey sought patterns that could betray the nature of the invisible force. Each dataset converged on the same haunting truth: roughly 70% of the cosmos is composed of something unknown, a force that cannot be touched, weighed, or captured in a laboratory. Its existence is known only through the way it shapes the universe. To study dark energy is to study absence, to infer reality from silence. It is like tracing the outlines of a predator never seen, known only by the disturbances it leaves in the forest. The galaxies are its pawprints, the microwave background its distant call, the supernova its fleeting shadow. The more carefully astronomers measured, the more undeniable the presence became. And yet, the more undeniable it became, the less it could be explained. Some suggested it was Einstein's cosmological constant, fixed property of space-time itself, an eternal pressure written into the geometry of the universe. Others speculated it might be a dynamic field, shifting and evolving, a relic of quantum fluctuations from the dawn of time. Still others feared it could be something far stranger, something not yet imagined. But all were united in one realization. Humanity now lived in a universe that was mostly unknown. The familiar stars, planets, galaxies made up less than 5% of reality. Dark matter accounted for a quarter more. But the rest, the dominant share, was this unseeable force. Stretching the cosmos into an uncertain future, the shock deepened with every refinement. Planck's exquisite maps of the microwave background narrowed the numbers, reducing uncertainties, but never removing the mystery. The dark energy survey traced the growth of structure, finding consistency but not explanation. The Hubble constant tower. Measure of expansion became a point of tension, with different methods producing values that disagreed. Some began to whisper of cracks in the standard model of cosmology, signs that the story may be even stranger than dark energy alone. It was as though the closer science came to measuring the immeasurable, the more the cosmos resisted understanding. Every new instrument confirmed the enigma, yet none could unravel it, and so the narrative grew darker. For while black holes were once the symbols of cosmic dread, at least they could be described, predicted, as contained within Einstein's equations. Dark energy was different. It was diffuse, omnipresent, unbound. It was not a monster at the edge of the galaxy, but a hidden ocean in which the entire cosmos floats. 70% of everything, 70% of existence, a majority share of reality itself, and yet no direct detection, no tangible evidence beyond the patterns it leaves behind. Humanity had unveiled the greatest discovery of the age, and in doing so, discovered how little it knew. The telescopes continued their vigil. Hubble, though aging, still peers into deep time. Chandra still listens in X-rays, where the maps of WMAP and Planck remain as cornerstones of cosmology. And the dark energy survey has given way to even grander instruments, like the Vera Rubin Observatory, preparing to chart the sky in motions and changes never before tracked. But even as the data accumulates, the question remains: what is this force that dominates the universe, yet refuses to reveal its nature? Is it a constant, eternal, and unchanging, or is it evolving, hinting at futures even stranger than scientists now imagine? The cosmos does not answer, it only accelerates. Galaxies drift farther, light stretches thinner, the void deepens. The measurements grow more precise, but the truth does not draw nearer. It is a paradox of human knowledge. The more clearly the universe is measured, the more profoundly its mysteries are revealed. To weigh the unseen is to confront the boundaries of understanding. To map the fingerprints of dark energy is to admit that the monster lies not beyond the horizon, but within the very fabric of space. And in that silence the question lingers: what does it mean to exist in a universe where most of reality cannot be known? The story of dark energy might have ended in resignation, a force unknown, but steady, a mystery locked away in numbers and equations. Yet as theories deepened, the mystery did not remain static. It grew darker. For some physicists began to suspect that the universe is not only ruled by an unseen hand, but that this hand itself may be unstable, trembling, ready to vanish without warning. The cosmos, in this view, is not resting on solid ground. It is perched instead on a false foundation, a delicate plateau of energy fields that only pretends to be stable. Physicists call it the false vacuum, a condition that seems permanent but is, in truth, precarious. If disturbed, it could collapse into a true vacuum, a lower, more fundamental state of reality. And in that collapse, everything we know would be erased. This speculation arises not from imagination alone, but from the mathematics of quantum fields, the standard model of particle physics. The most successful description of the subatomic world predicts that the Higgs boson, the particle discovered at CERN in 2012, sits in a peculiar position. Its measured mass suggests that our universe may not be in the deepest valley of stability, but on a ledge, a metastable state. Like a ball resting in a shallow dip, it is secure only until the right fluctuation, or some unknown trigger, pushes it into descent. If such a collapse were to occur, it would not begin with warning. It would start with a bubble, microscopic, invisible, expanding at the speed of light. Within that bubble, the laws of physics would be rewritten. The constants that shape chemistry, biology, and stars themselves would change in an instant. Particles would dissolve, atoms would fail, matter itself would disintegrate. Outside the bubble, reality would remain as it is, unaware of the coming tide. But as the bubble expands, no force could resist it. Black holes, galaxies, every living memory would vanish into the new order. This is not destruction in the way of fire or collapse. It is annihilation at the level of existence itself, a redefinition of what is possible. The universe would not end in violence, but in transformation, so absolute that nothing of the old could survive. Compared to this, black holes appear almost merciful. They are killers bound to their regions, executioners with horizons and borders. Their gravity devours only what strays too near, but a false vacuum collapse would recognize no boundaries. It would not wait at the edge of a galaxy. It would sweep across the cosmos universally, rewriting space-time itself. The terror lies not only in its scale, but in its silence. Because the bubble would travel at the speed of light, no observer could ever see it coming. The moment it reached a world, its physics would change in an instant, without anticipation, without suffering, without escape. One moment the universe as known, the next a reality entirely alien. The thought unsettles even seasoned physicists. For if this speculation is true, then the cosmos carries within itself a seed of inevitable annihilation. No black hole need approach, no gamma burst need fire. The danger lies not in distant catastrophes, but in the instability of existence itself. And yet there is a strange calm in this terror. If vacuum decay is real, it may already have happened long ago in some remote corner of the universe. So, the expanding bubble may even now be racing toward us, unseen, inevitable. Its arrival would be instant, its conquest complete. By the very laws of relativity, we could never know until the moment it was upon us. This speculation does not rest on fear alone. It emerges from attempts to reconcile quantum mechanics with cosmology, from the mathematics of fields that define reality. The Higgs field, which gives particles their mass, is itself a delicate structure. Its measured parameters suggest that the universe may not be resting in the most stable state possible. Quantum fluctuations, tiny tremors in the energy landscape, one day be enough to trigger its collapse. Some physicists argue that high-energy events, like collisions of cosmic rays or black hole evaporation, could seed such a decay. Others caution that the probabilities are vanishingly small, that the timescales may exceed even the lifespan of stars, yet the possibility remains. Haunting the equations, the thought is sobering, that the cosmos may not only be expanding, not only accelerating, but carrying within itself a hidden countdown. Not a countdown measured in seconds or centuries, but in quantum instabilities that care nothing for time. It is a reminder that human understanding is provisional. The very models that describe particles that predict forces also whisper of fragility. They suggest that existence is balanced precariously, not upon rock, but upon glass. Here, comparison to black holes returns with new weight. For while a black hole consumes and destroys, it also obeys. It follows the laws of relativity. It can be predicted, modeled, anticipated. Vacuum decay, by contrast, is lawless in its execution. It destroys not according to rules, but by changing the rules themselves. This is why the mystery escalates. Dark energy was already a force unknown, an engine driving the cosmos apart. But its nature may be tied to something even deeper, even more unstable. If the acceleration of the universe is linked to quantum fields, then its destiny may not be steady expansion, but sudden collapse. To live in such a universe is to live with humility. It is to recognize that existence is not guaranteed, that the ground beneath reality may shift without reason or warning. It is to acknowledge that the monsters of the cosmos are not only objects of mass and gravity, but the invisible fragility of space-time itself. And yet there is also perspective. If vacuum decay comes, it will be instant, without fear, without suffering. The universe will not end in screams, but in silence. Perhaps in that silence lies not cruelty, but inevitability, the turning of a page in a book, too vast to comprehend. Still, the possibility reshapes the imagination, forces the question. If reality itself is unstable, what does permanence mean? If laws can collapse, what meaning can be anchored in them? The escalation of the mystery is not only scientific, but philosophical. For in the shadows of dark energy and vacuum decay, humanity confronts not only the fate of stars, but the fragility of truth itself. The black hole remains a terror of the cosmos, but compared to the instability of space-time, it is only a shadow. On the surface, the deeper monster is silence itself, waiting in the vacuum, patient, inevitable, absolute. The universe has always been a theater of competing ideas, a place where mathematics and imagination converge to wrestle with the unknown. In the silence of deep space, where the stars drift farther apart and galaxies dissolve into the abyss, one truth is unavoidable. Dark energy is real, and it dominates the cosmos. But what it is, what shape it takes, what destiny it prescribes, remains a battleground of theories. Each model is a different monster, imagined in the language of physics. Some are steady and eternal, others unstable and apocalyptic. All are unsettling. The simplest vision is the cosmological constant. First proposed by Einstein in 1917, he had crafted general relativity, geometry where mass and energy curve spacetime, and spacetime in turn guides the dance of matter. Yet when he applied his equations to the cosmos as a whole, he found a problem. The universe should not remain static. Under the relentless pull of gravity, it should collapse. To preserve the notion of a stable, eternal universe, Einstein added a term, a repulsive pressure, that perfectly countered gravity on the largest scales. It was a balancing act, a mathematical patch. When Hubble discovered the expansion of the universe, Einstein abandoned the constant, calling it his greatest blunder. Yet decades later, in the light of accelerating galaxies, the constant returned from exile. Perhaps the simplest answer was the correct one, a fixed energy of the vacuum itself, an invisible pressure that does not change, woven into the very geometry of spacetime. In this picture, dark energy is not dynamic or evolving, but eternal. It was always there, and it always will be. But simplicity is not certainty. For quantum field theory predicts vacuum energy too, but in quantities that are catastrophically wrong. Calculations suggest values 120 orders of magnitude larger than what cosmology observes. The mismatch is staggering, the greatest known discrepancy between theory and measurement in all of science. If the cosmological constant is the answer, it is an answer that arrives with no explanation. A number inexplicably small, yet non-zero. Why should the universe's fate hinge on such a fragile balance? Why should existence depend on a constant so finely tuned? For some, this unease invites a different monster, quintessence. Instead of a static constant, quintessence imagines a dynamic field, one that evolves over time. Like the inflattened field that drove the universe's rapid expansion in its first instant. Quintessence would be a pervasive energy spread across space. But unlike inflation, it would not vanish quickly. It would persist, its influence waxing or waning as the cosmos matures. If true, quintessence might allow for futures stranger than steady expansion. Perhaps the repulsion will fade, allowing gravity one day to reclaim dominance, pulling galaxies back toward a final collapse. Or perhaps it will strengthen, driving the universe toward the abyss more violently than ever imagined. The shape of this field, its potential energy curve, would dictate the script of cosmic destiny. In this vision, the universe is not simply a stage, but a story unfolding, its ending unwritten. From quintessence arises an even darker speculation: phantom energy. This scenario imagines an equation of state more extreme than a cosmological, constant with pressure so negative that the repulsive effect grows inexorably stronger. Unlike quintessence, which might fade or balance, phantom energy accelerates without bound. The result is the dreaded Big Rip. In that nightmare, galaxies first drift apart, then stars are torn from galaxies. Solar systems dissolve, planets stripped from their orbits. In the final moments, even black holes disintegrate, their horizons shredded. Atoms themselves are stretched until they collapse. The fabric of space-time is torn, the cosmos not merely expanding but rending itself into pieces. Time does not end with silence. It ends with shredding. The phantom model is mathematically consistent with observations, but profoundly unsettling. It describes a cosmos doomed not by heat death, not by collapse, but by a catastrophic acceleration that dismantles all order. Here, dark energy is not merely a quiet tyrant, but a ravenous one. Growing hungrier as it devours, yet another specter arises from the Higgs field. Discovered in 2012 at the Large Hadron Collider, its measured properties suggest a universe precariously balanced in a metastable state. In this picture, dark energy may not be eternal, nor even evolving gently. Instead, space-time itself could be unstable, perched in a false vacuum. A quantum fluctuation could one day trigger its collapse, birthing a bubble of true vacuum. Inside that bubble, physics itself would be rewritten. The constants of nature, the strengths of forces, even the masses of particles would shift into alien values. Chemistry would fail, atoms would disband, and no trace of the old universe would remain. The bubble would expand at the speed of light, unheralded, unstoppable, extinguishing reality in silence. If phantom energy promises a violent tearing, false vacuum decay promises a quiet erasure. Both offer oblivion, but in profoundly different keys. In the search for understanding, some turn to an even broader canvas: the multiverse. If the cosmos is not singular but one bubble in a foaming sea, then perhaps dark energy is merely the property of our particular bubble. Other universes may exist with different constants, different fields, different fates. In some, dark energy might be negative, pulling space into collapse. In others, it might be too strong, preventing galaxies from ever forming. We inhabit the rare bubble where dark energy permits stars, planets, and life. This anthropic reasoning offers no comfort. It implies that our universe is not inevitable, but accidental. It suggests that the monsters of theory are not errors, but reflections of countless other realities where the story plays differently. And if our bubble is metastable, one day it may dissolve into a deeper state. It's collapsing into a truer universe that erases us utterly. Each theory offers not clarity, but a different shadow. The cosmological constant is eternal, yet inexplicable. Quintessence is dynamic, but uncertain. Phantom energy promises apocalypse by shredding. Vacuum decay whispers of sudden erasure. The multiverse frames all of them as accidents, cosmic lottery tickets drawn from an infinite deck. In the face of these models, black holes seem small again. Their ferocity is known, their mathematics elegant, their threat contained. The monsters of theory, by contrast, are cosmic in scope. They do not consume matter. They redefine reality. They do not kill within horizons. They dictate the fate of the entire universe. And yet, there is beauty in these speculations. They reveal the humility of science, the recognition that understanding is always provisional. Each theory is a map, drawn not of territory but of shadows, sketches made by light too faint to see directly. To contemplate them is to stand at the edge of knowledge and gaze outward into possibilities that may never be testable, but which nonetheless define the questions we must ask. The universe, in its silence, does not reveal which monster is real. It only accelerates, its galaxies drifting ever farther apart, its voids deepening. Whether the end is steady expansion, catastrophic ripping, sudden collapse, or eternal silence remains unknown. But in the speculation lies meaning. The monsters of theory remind us that existence itself is fragile, that the universe is not a fixed stage, but a shifting sea. And they remind us that the greatest terrors are not always the ones we can see, but the ones we cannot force woven into the very vacuum, silent, omnipresent, waiting. The cosmos accelerates in silence, its expansion driven by a force no eye can see, no hand can touch. Yet humanity does not rest in the face of mystery. It builds instruments of exquisite precision, machines that stretch imagination into steel, and glass designed to measure the immeasurable. If dark energy is the unseen tyrant of the universe, then these are the lanterns lit against its shadow, high above Earth. A new telescope prepares to take its place among the sentinels. The Euclid mission, launched by the European Space Agency, is crafted for a singular purpose: to map the geometry of the universe with unprecedented clarity. By tracing billions of galaxies across 10 billion light-years, Euclid seeks to chart how structure has evolved under the hand of dark energy. It measures cosmic shear, the subtle bending of light by gravity, and the clustering of galaxies, searching for the faint fingerprints left by the repulsive force. Each observation is not just an image, but a point on a map of the unseen, cartography of shadows that might one day reveal the nature of the unknown. On the ground, a colossal eye is rising in the mountains of Chile, the Rubin Observatory. With its vast 8.4-meter mirror and its camera the size of a small car, will conduct a survey unlike any attempted before. Night after night it will scan the entire sky, building a living archive of change. Galaxies drifting, supernova erupting, stars shifting in brightness, all will be recorded. By comparing these changes across years, Rubin will capture the growth of cosmic structure itself, testing whether dark energy is constant or evolving. Its data will be a film of the universe in motion, a slow unfolding of the cosmos written frame by frame. Beyond both, James Webb Space Telescope peers into a different frontier. Though not designed primarily for dark energy, it's infrared. Eyes reach farther back in time than ever before, glimpsing galaxies formed when the universe was young. By studying their distribution, their shapes, their faint glow stretched by expansion, Webb provides another piece of the puzzle. The early cosmos, with its first stars and galaxies, becomes a laboratory for testing whether dark energy was always present, or whether it emerged later, growing in strength as time advanced. But even telescopes cannot answer all questions. 2. Probe the possibility of vacuum metastability. Humanity turns not to the sky, but to the smallest scales of matter. At CERN, the Large Hadron Collider smashes protons together at near-light speeds, recreating conditions close to those of the early universe. In 2012, it revealed the Higgs boson, confirming the existence of the field that gives mass to particles. Yet its measured properties hinted at something unsettling, that our universe may not rest in a stable vacuum, but a metastable one, perched precariously above a deeper state. Experiments continue, searching for precision in the Higgs behavior, for whispers of other particles that might stabilize or destabilize the cosmos. Each collision, each spray of fragments, carries within it the potential to reveal whether space-time itself is secure, or whether it hides the seed of its own undoing. Still, the search does not end there. If dark energy is woven into space-time, then perhaps its influence ripples. The Laser Interferometer Space Antenna, LISA, a future mission led by ESA and NASA, will listen for gravitational waves across the solar system. Unlike LIGO and Virgo, which hear the violent chirps of colliding black holes, Lisa will detect waves of lower frequency, stretching across millions of kilometers. These waves may reveal new physics, disturbances in spacetime that carry hints of hidden fields. If dark energy interacts with gravity in unexpected ways, Lisa might be the first to hear its faint cosmic echo. The effort is monumental. Telescopes survey billions of galaxies. Satellites map the relic light of the Big Bang. Colliders recreate the first instance of creation. Detectors wait in silence for ripples from the invisible. Humanity has woven a web of instruments across sky and earth, all straining toward the same enigma. Yet despite all this, the numbers do not add up. The Hubble constant, the measure of cosmic expansion, remains divided between methods. Supernova and Cepheid stars suggest one value, the microwave background another. The difference grows sharper as measurements improve, not weaker. Some interpret this as a sign of hidden physics, a clue that dark energy may not be as simple as a constant. Others argue for errors not yet uncovered. But the tension persists. It's a fracture in cosmology that refuses to close. Even within the most precise models, uncertainty lingers. Is dark energy truly constant, or does it evolve with time? Is it a property of spacetime itself, or the manifestation of a field not yet known? Could it be linked to quantum fluctuations, or to dimensions beyond perception? Each dataset narrows the possibilities, but none delivers an answer, and so the pursuit continues, relentless and humbling. The greatest instruments of science point outward into the abyss, not for certainty, but for constraint, for the drawing of boundaries around ignorance. They reduce the range of what dark energy could be, but they do not reveal what it is. It remains a phantom, present in every measurement, yet absent in every explanation. In this struggle lies a deeper truth, that humanity has reached a horizon of knowledge. The cosmos is not easily unveiled. It guards its secrets behind light, stretched thin across billions of years behind particles that flicker into existence for fractions of moments. To measure the unseen is to press against the limits of what is possible, to build machines so delicate they can hear space-time itself tremble, so vast they can photograph galaxies as they were near the dawn of time. And still the mystery remains. The universe accelerates. Galaxies flee. The void deepens. The numbers resist harmony. The monster in the vacuum does not reveal its face. Yet this, too, is meaning. The pursuit itself is a testament to the fragility and strength of intelligence. Against a universe ruled by silence, humanity responds not with surrender, but with instruments, with equations, with the will to know. Now, though the unseen resists, the search continues. A dialogue between light and darkness written across generations. Perhaps the answer will come not as revelation, but as refinement and narrowing of possibilities until only one remains. Perhaps it will come as surprise, a discovery so alien that all models must bend. Or perhaps it will never come, and the universe will accelerate into eternity, its secret never spoken. But for now, the struggle continues. Euclid maps, Rubin watches, Webb peers, the collider smashes. Lisa waits, humanity listens. And the silence of dark energy endures, patient, absolute. Fear in the cosmos has always worn the face of the black hole. They are the dark giants, swallowing light, distorting time, devouring matter with an indifference so absolute it borders on cruelty. They inspire terror because they are visible. In their violence, dramatic in their hunger, inevitable in their pull. They are the predators of galaxies, and for generations they were thought to be the ultimate monsters of creation, but black holes. For all their might, consume only what drifts. Too near? Their horizons are boundaries, their power contained. They are local terrors. Beyond them, the universe remains untouched. Their hunger is vast but not infinite. Their reign, terrifying as it may be, is defined by edges. Dark energy is different. It does not roar, does not bend light in violent arcs, or shred stars in public spectacle. It is quiet, invisible, everywhere. It does not consume with hunger, it consumes with distance, pushing galaxies apart, erasing connections, stretching the bonds that hold the cosmos together. It terrifies not because it is violent, but because it is inevitable. It is not an event to fear, but a background in which all events unfold. And if vacuum decay is real, then fear itself deepens. For this is not a monster that waits in shadows, but a silence at the heart of existence. It is not the end of stars or galaxies, but the end of laws. The unraveling of physics itself does not destroy, it rewrites. It does not kill, it erases. Here lies the true terror, that the universe may not be eternal, but fragile. That the laws that govern every heartbeat, every orbit, every thought, may be temporary scaffolds. That space-time, so vast, so certain, may collapse without warning into something else, something alien, something in which no memory of this reality survives. Humanity lives suspended within this paradox. It gazes at the stars with wonder, yet beneath that wonder lies uncertainty deeper than any ocean. The cosmos is not secure ground. It is a shifting floor, perhaps stable for billions of years, perhaps not stable at all. Beneath the silence of the night sky, fragility whispers, and so the reflection turns inward. If the universe can end not with fire or collapse, but with silence, if it can vanish without trace, without witness, without warning, then what meaning can be found in the brief spark of awareness that flickers within it? Perhaps the meaning lies not in permanence, but in presence. To exist in a universe that may dissolve is to recognize the value of every instant. To think, to love, to wonder against the backdrop of a cosmos that offers no guarantee, this is a defiance more profound than survival. For even if the stage collapses, the play was still real while it was performed. There is awe in this fragility, a recognition that the cosmos does not promise safety, but it does grant moments. And in those moments, intelligence can bloom, questions can be asked, stories can be told. The monsters may be woven into space-time itself, but so too are the sparks of awareness that contemplate them. Black holes will continue to terrify. Their shadows cast across galaxies, their gravity pulling stars to their end. But greater still are the monsters without form, the dark energy that stretches the void, the false vacuum that may erase reality, the silence that rules 70% of existence. They do not consume light, they consume certainty. They remind us that the universe is not a fortress, but a fragile breath, suspended between creation and annihilation. And yet to know this is not despair, it is humility. It is the recognition that existence itself is extraordinary, not because it lasts forever, but because it happens at all. To live in a universe with fragile laws is to live in a miracle. To wonder at stars, to write equations, to measure galaxies against the void, these are acts of meaning carved into the face of imprimatur. In the end, the cosmos may end not with a roar, but with a whisper. But in the brief interval between, beginning in silence, consciousness arose and asked questions. It looked into the abyss and named its monsters. It dared to measure the unseen, dared to imagine futures, even apocalypses. It dared to reflect on its own fragility, and in that daring lies something greater than fear. It lies the quiet triumph of awareness itself, the fragile spark that, however briefly, illuminated the shadows. 4 black holes may be monsters, but they are not the greatest. The true monsters are written into space-time itself, hidden in the vacuum, silent, patient, universal. Yet even in their presence, humanity lifts its gaze and asks, what is the meaning of being here now, in a universe that may not endure? Perhaps the answer is this: that meaning is not granted by eternity, but by existence. That even if the cosmos is fragile, awareness within it is real. That in the silence before the end, the act of asking the question is itself the reply. And so the story closes not with terror, but with awe. The universe is vast, mysterious, and unstable. But within its shadows, something remarkable has emerged: the ability to wonder. That is the light that no monster can erase.